Hey everyone, Morgan here. Welcome back. We're going to be talking about bonding today. And this is going to be the first couple pages of the new AP Chem outline called Bonding and Lewis dot Structures. So make sure you have a copy of those. And it's kind of going to be just a grand tour of the types of bonds that exist inside of molecules and a little bit of an introduction to some very simple Lewis dot structures. Okay? So let's begin with Coulombs Law because that's what all of chemistry is. It's just an application of Coulombs Law. The force of attraction between two charged particles equals a constant K, and we really don't care what the number is because we're not solving the equation, times Q1 times Q2. Those are the individual charges of the two particles that we're talking about, divided by the distance between them squared. So what this is telling us is that Coulomb's law is a direct proportion between the size of the charges and an inverse square law when we're talking about the distance separating them. Okay? So again, this is going to come back into play. So our big question really is, why do two atoms come together and form a molecule in the first place? And what the answer comes down to is stability. The atoms are together. When they're together, they're more stable than when they are apart. So energy is released. So we're going to create an energy profile that talks about this. So here are my axes. And we're going to plot energy on the y-axis and the distance between the particles on the x-axis. And what this is going to end up looking like is this. And oftentimes we will refer to this as the energy well. Now, what are we representing here? Well, when I've got two particles very far apart, there's not going to be much attractive force between them. Okay? Now, as they come together, what will happen is we'll get to a specific distance where the attractive forces between the protons in one atom and the electrons in the other atom are at a maximum. And the repulsive forces between the electrons in the first atom and the electrons in the second atom are at a minimum. And that's going to be this distance right down there. And what this ends up being called is the bond length. It is how far apart those atoms are when you have maximum attraction and minimum repulsion. Now, if I brought those atoms any closer together, the protons from the first atom and the protons from the second atom are going to repel and push apart. So that's why that's a high energy situation. That minimum right there, that is where things are the most stable. And that tells us an awful lot about the molecule. Those are important graphs. All right? Now, a covalent bond is based on this idea. A covalent bond is equal sharing of electrons between two atoms. Now, the electrons that we're talking about are the valence electrons, or the outermost S and P electrons. Okay? Co means to share. Valent comes from valence, which means outermost. All right? Now, that happens only when the two atoms have what we call an equal attraction or pull on the electrons. And that gives us the concept of electronegativity. Now, electronegativity is the ability of an atom to attract electrons to itself when it is part of a compound. The ability of an atom to attract electrons to itself when it is part of a compound. Now, I would strongly recommend that you do some historical reading about Linus Pauling and the work that he did at Caltech. It was really seminal work on chemical bonding. In fact, he's got a book, I think it was about 3 editions, called The Nature of the Chemical Bond. I'm sure there's a copy of it on the shelf there behind me somewhere, okay? And really, really great work about how molecules come together, and eventually led to a Nobel Prize for Pauling in the early 50s. Now, what he did was had graduate students working with him measure the different bond lengths for homonuclear diatomics like H2 and then a heteronuclear like HCl, and compare the difference in the bond lengths and use that to determine what the overall attractive force was for that atom to have on the electrons. Now, we look at a periodic table. What we know is that down here in the left, we have very low electronegativities, and up here in the right, they are high. Fluorine is the very most electronegative element. Its value happens to be 4.0. That'll always be provided for you, of course. And cesium and francium are the lowest. And you see that in the table that I've given you. I think those are 0.7s. So what generally we're saying is that as you go across and as you go up, electronegativities are going to increase. Now, that's almost all we need to know. The numbers themselves, see, because what we can do is we can just look at how far apart the elements are, and that tells us the difference in the electronegativities for those elements. Okay? Now, you can have a situation where 2 atoms come together, they form a covalent bond, but the differences in the electronegativities is a little big, which means that it truly isn't a covalent bond, but it is a polar covalent bond. A polar covalent bond is unequal sharing of electrons in a covalent bond. So basically what we're saying is that one of the 2 atoms is an beautiful example of this. We know that the electron density in water is much closer to the oxygen than it is to the hydrogen. Okay? Now, one other definition, and to be honest, I really don't know where to stick this in the outline, so I'm just going to put it here, is the idea of a coordinate covalent bond. And a coordinate covalent bond is a bond where both electrons are donated by the same atom. Now we're going to talk about that a lot in this chapter, and it's going to introduce a concept called Lewis acids and bases, which we did actually talk about in our very first unit a little bit. So both the electrons that are involved in the bond come from the same atom. Okay, now that's the end of the first page. Freeze the video if you need to get something copied down, but we're going to move on to the next page. Page 2. Now, we know that ionic bonds are attractions of positive to negative. We know that it's a Coulombic attraction or an electrostatic attraction. A lot of books say, this is especially true in biology books, that an ionic bond is when one element transfers electrons to another. We don't know that to be true, okay? That may not be true. We've got the Heisenberg uncertainty principle to deal with here, okay? So let's not say it that way. We'll just say that ionic bonds are attractions between oppositely charged particles, okay? Now, there's a scale for us to help understand whether a bond is going to be covalent, polar covalent, or ionic. So, this is going to be the difference in electronegativity, delta En. From 0 to 0.2, from 0.2 to 1.7 and above. If it's below 0.2, most books say it is a covalent bond. If the difference is between 0.2 and 1.7, most books say polar covalent. And above 1.7, ionic. Now, I gotta be honest with you, I have a problem with that. This is not really 100% true. Are there any truly, purely covalent bonds? The answer is yes, for sure. Homonuclear diatomics, H2, O2, F2, etc. Perfectly equal sharing. Now, if you have two atoms that are different, but have the same electronegativity, when they bond, the atoms are different sizes. So Coulombs Law is going to come into play here, and we're not going to have perfectly equal sharing. So truly, the only covalent ones would be molecules like F2. Now, 0.2 to 1.7. Well, the textbook by Zumdahl that I've been teaching out of for a long time, those were the numbers. But in other textbooks, different scales. I've seen 0.4 to 1.9. This is a recommendation. This is a way to kind of understand what's going on. Now, above 1.7, let's say it's ionic. Well, that's not totally true either. See, it turns out compounds like lithium fluoride are the very most ionic compounds that we know of. And when measured, only 69% ionic character in lithium fluoride. Now, what's going on here? Well, if you put two atoms, even if they're ions, side by side, are they going to share electrons a little bit? I mean, come on. You get along with your siblings sometimes, right? I'm not saying all the time, but sometimes, okay? You put those two atoms side by side, they're going to share electrons a little bit, okay? So what does this mean? Well, I can't just say it means everything is polar covalent, okay? But it's the extent. When you're really not very polar covalent at all, we call it covalent. And when you're really, really polar covalent, we call it ionic. It's just to what extent is the sharing equal or unequal? Really, really unequal, much closer to equal. Okay? Now, I'll show you some math problems just to make you feel at ease. F2. Can we determine whether it's covalent or not? Sure. Take the difference in the electronegativity. Delta equals, well, the first fluorine is a 4.0, and the other fluorine is a 4.0. So 4.0 minus 4.0, I got a calculator here if necessary, but that's 0. That is truly a covalent bond. Now water, which we already know to be polar covalent. In fact, if you look up your AP Bio book from last year, I'll bet you chapter 2 or chapter 3 was probably called Water, the Universal Solvent. And that's because of its polar covalent nature. Okay? The oxygen is a 3.5 minus a hydrogen is 2.1. You don't multiply this by 2 because there's 2 hydrogens, because we're really just looking at the bond between the oxygen and one hydrogen. Okay? One bond. So only 2 atoms will ever be involved. 3.5 minus 2.1 equals 1.4. So we say that's polar covalent. Falls right in there in the scheme of things, right in there. Okay. Now, for HCl, chlorine is a 3.0. So delta equals 3.0 minus 2.1. If you're wondering which one goes first, I just put the bigger one first, so the number always comes out positive. That way I don't have to do an absolute value. That difference is 0.9, which means polar covalent. But isn't it funny that back in the first chapter of the year, when we talked about HCl, we talked about it as a strong acid, something that fully dissociates when we put it into water. So some people might think that that means it's an ionic bond. It's not. It's just a pretty polar covalent bond. Okay. Now KCl, we're getting into some bigger numbers here. Okay. For the potassium, it's 3.0 minus 0.8. That equals 2.2. That's pretty darn ionic. Okay? Now, I think I forgot to put CH4 here. Let's move CH4 in. Methane. We always use methane as our example of a great covalent bond. Got some interesting news for you coming up. Okay? Carbon. On the table that's in the lecture outline, that's a 2.5. So we have a 2.5 minus 2.1 equals 0.4. And by almost all scales, that is polar covalent. Okay? And then the last one was NO2. Oxygen is a 3.5. Sorry, 3.5. Nitrogen, I think that's a 3.0. Let me look at the table for a minute. Yep, 3.0. That equals 0.5 polar covalent. Now, those tables will be available to you when you need them, but really all you have to do is look at how far apart are they. Okay. Now what we're going to be doing is going back and looking at some very basic Lewis structures. Okay, and we've done these before, so we can get through these relatively quickly. We know that our goal is to try to put 8 electrons around each atom when we can. That is going to be what we call the octet rule. For hydrogen, duet's fine. Because for most atoms, they just have outermost s and p orbitals, 2 electrons in the s, 6 in the p, that makes 8, full shell, stable. For hydrogen, it only has a 1s orbital, 2 electrons, stable. Okay? I'm going to do these in color. I'm going to color code them just so to make it a little bit easier for you to see, but that's not required. Hydrogen. When I go to my periodic table here, hydrogen, it's in group 1, okay, which means it has 1 valence electron. So here's my hydrogen. I represent the 1 valence electron with a dot. It's just a representation. Okay. The other hydrogen has 1 valence electron. They share those 2 valence electrons. That's a covalent bond. Okay. Chlorine. Halogens are pretty boring in a sense. They have 7 valence electrons. So pretty much they're only going to form a single bond to other species. There are a couple exceptions we'll point out to you, but for now, that's good. So with 1 valence electron each that's unpaired and the other 6 are paired, this is much like hydrogen, and we share those unpaired ones. Now, if I look at this, this chlorine is surrounded by 8 valence electrons. That chlorine is surrounded by 8. That's great. That's exactly what we're looking for. Octets. Oxygen has 6. So the way I'm going to draw them is 2 pairs and 2 that are alone. And the hydrogens each come in with 1, H, boom, H, boom. There we go. Okay? Now, I think you know how to do this. I really do. So why don't you pause the video for a second, try and draw the next 6, and then tune back in. Okay, I'm sure you're done by now. Let's see what you've got. For methane, 4 valence electrons that belong to carbon, and then we'll have 1 each from the hydrogens. Boom, there they are, octet. I2, iodine, 1, 2, 3, 4, 5, 6, 1, other iodine, 1, 2, 3, 4, 5, 6. Now, some people might flip here that I drew them horizontally rather than vertically. Don't worry, it doesn't matter, it's just a representation, that's fine. Okay? Nitrogen with its 5 valence electrons in the blue, the hydrogens coming in green, and we've got a nice octet. Carbon. The 2 carbons side by side, each with 4. They're sharing the first one in there to bond to each other, and then the 6 hydrogens. Boom. CCl4, carbon in the middle, 4 valence electrons. The chlorines are very predictable because they're halogens. Chlorine, 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 chlorine. Now, some people would ask me at this point, what about exchanging 2 dots for a line? Officially, that means it's no longer a Lewis dot structure. It's a line structure or a Kekulé structure. The AP exam asks mostly for you to draw Lewis dot structures, so we're going to be drawing dots. Okay? Phosphorus, 1, 2, 3, 4, and 5. And then my chlorines. Boom. 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 And there we go. Okay, so that's the first 2 pages of this new outline. Pause if necessary. And then we'll pick up with the rest next week. All right, this is Morgan signing off. Thanks for tuning in.